So, hello everyone. My name is Jesse Ratzkin. I'm at the University of Würzburg in Germany, and I would like to tell all of you a little bit about a project regarding Q-curvature, which is related to scalar curvature. And before I begin, I would like to thank all the organizers for gathering everyone together virtually and providing us all with this forum. And I'm excited to share some mathematics with all of you. So, there's a brief sketch of what I'm going to tell you. There's an introduction. I'll state some theorems. I'll sketch some of the proofs, and then I will conclude everything. So I'd like to begin with some very brief remarks about scalar curvature, as this is a conference in honor of Gromov. I feel like one should at least mention his very deep contributions to the field. In particular, in collaboration with Lawson, Gromov famously proved, among other things, that the connect sum of two manifolds which carry a positive scalar curvature metric will also carry a positive scalar curvature metric. And then they had a very famous conjecture about conditions on which a manifold of dimension at least 5 can carry a metric of positive scalar curvature. There's a very long list of his contributions, and I can't attempt to summarize them all here. And I'm going to also tell you about some work on constant scalar curvature metrics within a conformal class. And this was really started by Hideo Yamabe in 1960, who asked whether each conformal class on a compact manifold admits a constant scalar curvature representative. So if you write your conformal metric in this way, as your g tilde is u to a certain power times g, the scalar curvature of the transformed metric ends up being given by this very nice differential equation you see listed here. And if you look at the form of this differential equation, you'll see that it involves this particular power. And if you multiply your equation for essentially this equation by u, you can write down the total scalar curvature functional, which ends up being this guy. So this is basically the integral of the new scalar curvature divided by a normalizing factor to make the whole quotient scale invariant. And this ends up being the integral of u times L of u divided by the LP norm of u, where p is equal to this critical exponent of 2n over n minus 2. And then, furthermore, one can define these invariants. This script y is the classical Yamabe invariant, and this is the infimum of this total scalar curvature functional over all metrics within a conformal class. And then, furthermore, one can define this boldface y, which is the supremum of the Yamabe invariant over all conformal classes. This is a differential invariant. And Yamabe proposed to solve his problem variationally by essentially regularizing this total scalar curvature functional and taking an exponent which is slightly smaller than the critical exponent. It's for each p less than 2n over n minus 2, one can show that this ratio has a unique minimizer, and then one can try to find these constant scalar curvature metrics by taking a limit of these minimizers as p goes to this critical exponent. And of course, The problem with doing this is that this exponent is exactly where one loses compactness in the subleft embedding. And we'll see an example of this loss of compactness very explicitly in a couple of minutes. So the short version of this is that over the next 25 years, many people worked very hard and tried many very creative things to solve Yamabe's problem. There were some partial results by Yamabe himself. There was an important step by Schrödinger and an important step by Theo Alban. And eventually, in 1985, Rick Schoen answered Yamabe's question in the affirmative. And what he showed is that this Yamabe invariant, this infimum, is always actually a minimum. And in general, this infimum, so Alban actually showed that this infimum is less than or equal to the quotient you obtain for the round metric on the sphere. And the round metric on the sphere is actually a minimizer of within its conformal class. But the difficult part, which is the part that Schoen did, is proving that equality in this inequality here can only occur if your conformal class is that of the round sphere. So there's an interesting thing he proved at about the same time, which is that if you look at the differential invariant, which is this supremum over an infima, this differential invariant on S1 cross Sn minus 1 is actually the same thing as the differential invariant on the n-dimensional sphere. We'll touch on, we'll see why that is very soon towards the end of the talk. There's a very simple reason why this equality must hold. I'd like to say that even though these results that I'm telling you at the moment are have been in the literature for a while, since the mid-1980s, that this is still very much an active area of research, and is still very difficult. So with that being said, I would like to now introduce this fourth order variant of scalar curvature. This is something called the Q-curvature. This was first written down by Stephen Panitz in the 1980s, and later Tom Branson did a lot of work on this. So there's a formula here, and the important things to pay attention to are the fact that this Q curvature is given by an expression which is essentially quadratic in the scalar and Ricci curvatures of your metric, and it has a leading order term which is essentially minus the Laplacian of the scalar curvature. And much like the scalar curvature, the Q curvature has a very nice transformation law. If I do a conformal change of metric, I have a slightly different exponent here, but otherwise everything is very much the same. If I do a conformal change of metric, then the Q curvature in this new conformal metric is given by u2 this power times a certain differential operator applied to u, and this differential operator has the form of the bi-Laplacian of u plus a divergence term, where this divergence term involves Ricci and scalar curvature, and the zeroth order term is the Q curvature. So much as in the case of scalar curvature, one can define the total Q curvature functional. It has this very nice form. one can define a conformal invariant by taking an infimum of this total Q curvature over all conformally related metrics, and one can define a differential invariant by taking a supremum of that infimum. So there are some decorations here to the script y and the boldface y. The 4 in the subscript is meant to indicate that I'm looking at a fourth order differential equation. The plus here in the superscript is meant to indicate that I want to restrict in this expression for the total Q curvature, I want to restrict to positive functions in this infimum. One can imagine trying to take an infimum of this ratio over here over all functions so long as they're not identically 0. And in the scalar curvature case, in the second order case, that infimum is automatically going, if it's realized, it's automatically going to be realized by a function which does not change sign by the maximum principle. In our case here, we have a fourth order operator, so we lose the maximum principle to some extent. And that means you really do need to restrict to positive functions. That's what this plus is supposed to mean. Okay, once again, it is fairly standard to show that critical points of the total Q curvature functional are exactly the constant Q curvature metrics in a conformal class. So the setup is very much like what we had for the classical Yamabe problem. Now, at this point, it is worthwhile to seriously understand the sphere. Much of the work in Q curvature takes its motivation from everything done in scalar curvature and the Yamabe problem and related problems like prescribed scalar curvature, etc. And in those problems, we have already seen that the round metric of the sphere is an important example. It serves as this important upper bound. So let's examine the case of the sphere. If I use stereographic projection to transfer this problem to Euclidean space, my differential equation, the differential equation here becomes this fairly nice differential equation, which is just the bi-Laplacian of u is equal to u to this power of n plus 4 over n minus 4. There's a constant here which makes some of the other constants work out much nicer, but that's decorative. It doesn't have much import. And one can find a solution very quickly. You just take the conformal factor from stereographic projection. You get this solution. You can rescale this solution to get these guys for any positive lambda and any point x naught. And in fact, in 1999, C.S. Lin proved that these spherical solutions here are all of the positive global solutions to this differential equation in the whole space of Rn. And a funny thing happens to these solutions when lambda goes down to 0. So you see essentially that all of the mass, all of the geometry of the sphere gets concentrated at the south pole, or at this point x naught. And what happens to these functions is that outside of any fixed neighborhood of x naught, the function will go to 0 uniformly, but at x naught, the solution will blow up, so you get a bubble. And the occurrence of these bubbles is exactly reflecting the non-compactness of the Sobolev embedding. Okay, so So one thing this tells you is that if you really want to understand the totality of solutions, the totality of all constant Q-curvature metrics in the conformal class of the sphere, or in the conformal class of any locally conformally flat metric, then you really must understand isolated singularities, because they come naturally as these limits. So toward this end, there's many people working in this, so I'll just highlight a couple of results. There's a very recent theorem from last year by Jin and Schoen, which says that if you have a smooth solution in a punctured ball, smooth positive solution of this differential equation, which is essentially bi-Laplacian of u is equal to u to the power n plus 4 over n minus 4. And this function is also superharmonic. This result says that u is very close to its spherical average. And if you want to phrase this geometrically, you would say that in the locally conformally flat setting, if you have a locally conformally flat metric with constant positive Q curvature and positive scalar curvature, so positive scalar curvature ends up implying this superharmonicity condition, then this metric must look more and more round, more and more rotationally symmetric as one approaches this singular point. So the first result I want to tell you about is a refined asymptotic statement. To make sense of this refined asymptotic statement, we first transform into cylindrical coordinates, and you do this change of variables. You let t equal minus the log of length x and theta x over length x, and then you define v of t and theta to be this guy. And once you do that, the PDE transforms into this, which looks, so this might look a little bit intimidating at first, but is really the Panitz operator, this P for the cylindrical metric, dt squared plus d theta squared, which one can compute, is a very straightforward computation. So you can find two solutions very quickly. The first solution you find is the constant solution. So you just make all of the derivatives equal to 0, and you set v equal to a constant. You find this particular constant here. So I'm going to call this constant epsilon bar. And it turns out that this epsilon bar is between 0 and 1, which follows directly from the fact that n is greater than 4. There's another solution you already know that comes from the sphere. And this solution has the very nice form of being cosh to the power of 4 minus n over 2. So several years ago, Rupert Frank and one of his PhD students, Koenig, classified all positive global solutions. So this is global on the whole cylinder of this PDE. And they found a very nice description. All of these solutions are periodic functions. They're functions of t alone. You can classify them by their maximum value at translate to make that maximum value happen at t is equal to 0. And they have a very nice description that they essentially interpolate. So there's the spherical solution we know, this guy here in green, which has a maximum at t is equal to 0 and then decays monotonely. There's the constant solution here in red. And interpolating between these, we have these nice periodic guys. So these will each have a period. One thing I want to point out here is that the period varies with epsilon. When epsilon increases, the period also increases. And we're going to call the solution whose maximum value is epsilon the Delaunay solution V epsilon with parameter epsilon. And we call its period T epsilon. So the next term in the asymptotic expansion of these singular solutions ends up being a certain translate of these Delaunay solutions. So you can find these translates by transforming back to the Euclidean coordinates and then translating infinity using the Kelvin transform. That's what this transformation does. So you essentially invert through a sphere, translate the origin, and then invert through a sphere again. That's what we're doing here. And if you carry out this computation, you'll find that these V epsilon A's have this particular form, but the important thing you should pay attention to is actually this expansion down here. You see that this V epsilon A is the original V epsilon plus something which decays like e to the minus t. And then the next order term is going to decay like e to the minus t. And this thing that decays like e to the minus t is a very explicit expression involving V epsilon dot and V epsilon. Okay, so the first thing I'm going to tell you is that the following. I have the same setup as in the Jin and Schoen, the same hypotheses as in the Jin and Schoen result. I have a smooth solution in a punctured ball. It's a positive solution. I want the function to be superharmonic. And then I'm going to define my V. This is now a function defined on the positive half cylinder where t is from 0 to infinity through this change of variables. And then under these hypotheses, either my original U extends to be a smooth solution, or I can write V as these translated Delaunays plus a remainder which decays like e to the minus beta t, where beta is something strictly greater than 1. So this is a refinement of the asymptotics, of the simple asymptotics I stated by Jin and Schoen. Next, I want to tell you a little bit about these conformal and differential invariants. So as in the case for the scalar curvature for the Yamabe problem, it's very difficult to actually compute any of these invariants. So one result I'd like to highlight is something by Fang and Yang, and Fenbo Hung, this should be Hung and Yang, and they proved the following. They said that if you have a compact Riemannian manifold of dimension at least 5, such that the classically Yamabe invariant is positive, the Q-curvature is greater than or equal to 0, but not identically equal to 0, then this conformal invariant is less than the value one obtains for the sphere. Equality can only occur if your conformal class is that of the round sphere. And in this case, this infimum over here, given by the conformal invariant, is actually realized. It's a minimum. There exists a smooth metric within the conformal class realizing this infimum. So there's an interesting example that comes if you understand the Delaunay surface, the Delaunay metrics I've just described, and is really summarized by this result, which says that if I equip S1 cross Sn minus 1 with the the product metric. I assume that my S1 factor has circumference capital T. Then the limit of these conformal invariants is equal to that of the round metric on the n-dimensional sphere. So in particular, the differential invariant, the four-dimensional differential invariant on S1 cross Sn minus 1 is equal to the differential invariant on Sn. So this is exactly the same as what Rick Schoen had proven in the case of scalar curvature. So there's an important observation, which is that by the theorem of Hahn and Young, this equality here, this supremum of infima, cannot be realized by a smooth metric, because that would violate their theorem. So I'd like to at least sketch the proof of the refined asymptotics. So it goes as following. The first thing you need to do is prove a priori estimates. So this was actually proven by Jin and Schoen, who says that if you have a U which satisfies the hypotheses that is bounded above and below by length of x to the power 4 minus n over 2. And if I translate this bound, these upper and lower bounds into my cylindrical coordinates, I obtain that my v is bounded between two positive constants. So now I can take what's known as a slide back sequence, which is I choose any sequence of tau k's going to infinity, and I just translate my v's by these tau k's. By these a priori estimates, I can extract a subsequence which converges uniformly on compact subsets. It must converge to a solution of my PDE in the whole space, but by the Franken-Koenig classification, I know all of those solutions in the whole space. They're exactly translates of the Delaunay solutions. So I know that some subsequence converges to these translates. And now what remains is essentially showing that the limit I obtain in this subsequence does not depend on any of the choices that I've made. It doesn't depend on which subsequence I chose of these VKs. It doesn't depend on any of these tau k's, any choice of tau k's going to infinity. No matter what choices I make in this construction, I will always obtain the same parameters, epsilon and capital T. So how does one do this? To do this, one really needs to understand the linearized Q-curvature operator when you linearize about a Delaunay solution. So I'm going to call this linearized operator L epsilon. So this is the linearization of the Q-curvature equation. I'll write it down more explicitly in a minute. And I want to understand the solutions, the tempered solutions of this linear fourth order PDE. So once I unwind what this convergence means, I can show, so once I unwind the convergence, that these VKs converge to the V epsilon, a translate of the V epsilon, I obtain these simple asymptotics, which looks like this, that the difference between V and my translate of the V epsilon decays like e to the minus alpha for some alpha, which is positive. And then once I have this simple, so this is my simple asymptotics. This is essentially the Jin and Schoen result. Once I have the simple asymptotics, the refined asymptotics follow from the linear analysis we did in this previous step here. So this whole idea of constructing a slide back sequence goes back at least to Leon Simon, where he wanted to understand possible limits of tangent cones of minimal surfaces one obtains by blowing up rescaling constant mean curvature surfaces in Euclidean spaces. This is a fairly classical and well-used argument. Later on, exactly this outline I just showed you was used by Corval, Matzel, Packard, and Schoen to obtain a refined asymptotic expansion for solutions of a singular Yamabe problem, as a constant scalar curvature equation with isolated singularities. Okay, so with that said, the important thing to understand is this linearized operator, L epsilon. So before we do that, it's maybe worthwhile to understand some of the properties, some of the geometry of the Delaunay solutions. So the Delaunay solutions satisfy this fourth order ODE, which looks like this. If I multiply that ODE by V dot and I integrate, I obtain this script H functional. So this is an energy, this is actually conserved. Now, on the face of it, it looks like this one energy functional should not be enough to specify a solution of my ODE, because after all, what I have here is an ODE. So you would imagine that I should actually need three energies, three different conserved quantities to do an effective phase space analysis of the ODE. But actually, and this is really very remarkable, I think, there's some work by Jan Bove van den Berg where he examined actually a fairly general class of fourth order ODEs, and he showed that essentially, if you restrict your attention to bounded solutions, they behave like second order ODEs. And this energy functional restricted to the VV dot plane determines the solution. He proved energy ordering if you have solutions with lower energy, they lie below the solutions with higher energy, etc. And the key step in the Franken-Koenig's classification proof is to show that that any positive entire solution must be bounded, so that one can apply this ODE analysis of van den Berg. Okay, so this means I can essentially draw a phase plane analysis of my ODE solutions. I see the cylinder solution is this point right here. This is the strict minimum for my energy. It's a negative value. The zero set of my energy is the union of the spherical solution, which is this blue curve here, excluding the origin. And if you want to have all of the zero set of my energy functional, I have to add in this stationary point here at the origin. In between the cylinder solution here in the middle and the spherical solution here at the boundary, I have leaves, these closed curves that give me all of these nice periodic solutions. These are the Delaunay solutions. Okay, and this page is just text explaining what I've just told you in the previous picture, one can show that all of the solution curves with positive energy cross into the left half plane where v is less than 0, so they can't actually give you conformal factors because your conformal factor should be positive. Okay, so if I want to understand mapping properties of this v epsilon, I decompose my functions into spherical harmonics, and then I end up with a family of fourth order ODEs, which is as follows. For the low Fourier modes, I can identify some of them very explicitly. So the V dot gives you one solution, and this is a nice bounded periodic solution of the J equals 0 mode, Fourier mode, and the derivative with respect to the Delaunay parameter gives you another solution of the 0 Fourier mode. Because the period is increasing in epsilon, this W0 minus is actually not bounded, it grows linearly, but they're still nice tempered. Both of these are still nice tempered solutions. The J equals 1 through n Fourier modes are all something one obtains by geometric translations. So essentially we've seen all of these modes. They come from taking the derivative of the translation in a coordinate direction. So you translate your Delaunay solution, and then you take a derivative of that with respect to the translation parameter, evaluated at tau equals 0. And when you do that, you obtain, when you translate the point at infinity, which was what I wrote down for my refined asymptotics, the thing you obtain decays like e to the minus t. If you don't translate infinity, but you translate a finite point, the point at the origin, for instance, you obtain a Jacobi field which grows like e to the plus t. And these are very explicit. So the key point is that the Jacobi fields are rising, excuse me, are rising from here, are tempered, and the Jacobi fields arising from here either grow like e to the plus t or they decay like e to the minus t. And what I would like to do is understand the exponential growth rates of all of these Jacobi fields. And in order to do this, I introduce something called the Fourier-Laplace transform. So it's fairly well known that, for instance, if you study the heat equation or the wave equation or the Laplacian in Euclidean space, that you can do much of that analysis by taking the Fourier transform. If your metric or your setting is not homogeneous but is periodic, then you can't really do that because you don't have enough symmetry around to do that. So to get around that, you use essentially a discretized sum, which is kind of playing the role of that Fourier transform. So this, the idea of using this Fourier-Laplace transform goes back, I think, to Cliff Taubes, and it was used by Matteo Pollock and Uhlenbeck in understanding the moduli space of singular Yamabe metrics. And more recently, it's been used by Alvaro Hernandez and Mikhail Kovalchik in trying to understand certain solutions of the Allen-Kahn equation. So there's something that looks a little bit funny about this for the Laplace transform, which is that I started with a function that depended on two variables, namely t and theta, and then I'm getting out something that actually depends on three variables, t, zeta, and theta. So why do I have this new variable? What role is it playing? The role it plays is that this new variable is allowing me to control the rate of exponential growth or decay of my solution. So the other thing one can show is that one can re-index the sum in my definition of this transform. And if you translate my t parameter by a period, you actually get this factor of e to the I zeta coming out in front. So if I chase through my definitions, this means I can now define an operator on S1 cross Sn minus 1 this way. And the whole point of doing this is that now I have a well-defined parameter between fixed function spaces on a compact manifold, and this operator depends holomorphically on my parameter zeta. And once I have this information, I can apply something called the holomorphic Fredholm theorem, which says that this L tilde is either never Fredholm for any value of zeta, or it's Fredholm so long as zeta stays away from some discrete set in the complex plane. So the next thing one can do is again decompose my transformed operator into Fourier modes and then reconstruct some bands of eigenvalues subject to these quasi-periodic boundary conditions. And in the case of the cylinder, the bands actually are very explicit. You have a band here that goes from 0 to 1, and a band here above 1, and then a band here that corresponds to this corresponds to the start of the other solution corresponding to the Fourier mode with j equals 1. And what I conclude is that actually the only tempered Jacobi fields for the cylinder are either the translations along the axis or the changing the Delaunay parameter. And once I have this information, I can essentially use bifurcation theory to show that because these spectral bands actually can't cross. I always have a band starting at 0 corresponding to the geometric Jacobi fields, which are translation along the axis and changing the Delaunay parameters. I always have another band starting at 1 corresponding to translation off the axis. So because I know that I always have those two bands, I know that my bands that start above 1 can't cross over. And that tells me that the same phenomena that I had for the cylinder must actually occur for all of these Delaunay solutions, namely the the only two tempered Jacobi fields are the ones that correspond to translating along the axis and changing the del and A parameters, these W0 plus and W0 minus. So once I see that whenever I choose my eta to be a real number between 0 and 2 pi, my L tilde of eta is actually injective. And that tells me I can construct a Green's function solution operator as long as I stay away from some discrete set of poles. So if I unwind this definition, I see that my original operator is Fredholm, and it has a well-behaved solution operator on my weighted function spaces, so long as my weight is not the imaginary part of some pole in this pole set. These sets of weights, these bad weights, so-called bad weights, are typically called indicial roots of the problem, of the indicial roots of the operator. And they give you exactly the exponential growth or decay rate of the Jacobi fields of L epsilon. So now, once I have this, I can, if I start with a right-hand side, F on my right-hand side, which is compactly supported, I want to solve L epsilon V equals F. I can try to solve on one side of an indicial root, and on another side of this indicial root, I'll obtain two different solutions, V plus and V minus. And the difference must actually be a Jacobi field, which decays with this exponential rate e to the minus gamma jt. So if I bootstrap this whole thing by moving my contour integrals up and down, I obtain an asymptotic expansion of my solution LV equals F, my solution V as a sum of these Jacobi fields, which decay like e to the minus gamma jt, where these gamma j's are my indicial roots. So the consequence of this contour shifting argument is what's known in the literature as a linear decomposition lemma. So it says that if I have a V which grows at most like e to the delta t, where delta is between 0 and 1, and a phi which decays like e to the minus delta t, and my LV equals phi, then my V must actually be something which decays exponentially plus something which is bounded and periodic plus something which grows linearly. So these are the solutions that we know. And then if I want to prove my refined asymptotics, I apply my linear decomposition lemma to the difference between V and my V epsilon plus T. Okay, so sorry, this is really the final step in the proof of the refined asymptotics. So I'd like to spend a couple of slides telling you a little bit about this, how you prove this result for the conformal and the differential invariant. So the idea is actually very simple. You take this product metric on S1 cross Sn minus 1, and you let G tilde be any conformally related metric. So it's going to be V times GT. And you extend this V to be a T periodic function on the whole cylinder. So if I want to find, because my cylinder satisfies all the hypotheses of this theorem by Han and Yang, I know that there exist solutions to this. I know there exist metrics with constant positive Q curvature. So I know there exist these solutions to my PDE on this whole cylinder, but by the Franken-Koenig classification, I know that all of these solutions must actually be translates of a Delaunay solution. Okay, so the question is then really, which Delaunay solution actually gives you the energy minimizer? But by a Strom-Liouville argument, the least energy solution is actually the one whose period matches this capital T, which is the circumference of this S1 factor, so long as this capital T is large enough. And what do you conclude? You conclude that this fourth order Yamabe invariant of this metric is equal to the Q curvature functional evaluated on the Delaunay metric. And then when I let my epsilon go to 0, which is the same thing as letting capital T go to infinity, I obtain convergence to the spherical solution. So here I'm using the fact that this V epsilon converges to the spherical solution on any uniformly on any fixed compact set as epsilon goes to 1. So that really completes the proof of this theorem about the conformal and the differential invariance. Okay, so I want to tell you some open questions. So the first fairly obvious one is the analog of the classical Yamabe problem. Does each conformal class on a compact manifold admit a constant Q curvature representative? So this is, it still needs a lot of work. For which Q can one prescribe this Q curvature? For which functions can you prescribe this Q curvature, for instance, on a sphere? For which closed sets on a sphere can you find the kind of singular solutions I've described? And everything I've said here has been about solutions with positive Q curvature, but there's no discussion of negative Q curvature. So there's something that's kind of interesting here, which is that the Q curvature of hyperbolic space ends up being the exact same as the Q curvature of the sphere. And so this is kind of an interesting phenomena. I'll tell you some references. The paper by Jin and Shang, one can find on arXiv. It was from January of this year. The asymptotics result I told you about is in this preprint, which is also on arXiv, and the result about the fourth order conformal invariant is in this paper on arXiv. There's a related result by Jean Andrade and Jean Dehaut, which is about conformally invariant fourth order systems where they derive some very similar asymptotic results, and their work is also very interesting. So I think that is worth looking at. And finally, thank you for your attention. And please, if you have questions, contact me at this address. Bye.